Have you ever stopped to think about electricity and magnetism? I mean, what do they really have in common? We use them all the time, but it turns out they aren't just separate forces of nature. They're actually two sides of the very same incredible coin. So today, let's pull back the curtain on this hidden connection and see how it literally powers our world.
So here's our game plan. We're going to start with a totally accidental discovery that changed everything. Then, we'll figure out how to see these invisible forces all around us. After that, we'll see how just changing the shape of a wire can create some serious power. We'll also unpack the hidden push that makes motors work, and finally, we'll bring it all right back home to the wiring inside your house.
All right, let's kick things off at the very beginning. We're talking about a single moment of pure chance that completely reshaped how we understand the universe. It all started with a pretty shocking connection.
You know, today we kind of take it for granted that these two are linked. But if you rewind to the early 1800s, this was a huge mystery. Electricity was all about sparks and currents, while magnetism was about weird rocks and compasses. They seemed like two totally separate worlds.
But then, in 1820, everything changed. A scientist named Hans Christian Ørsted was in the middle of a lecture, and he just happened to have a compass sitting near his electrical equipment. And when he flipped the switch on his experiment, he noticed something nobody had ever seen before. So get this. He passed an electric current through a plain copper wire, and the compass needle nearby, which, remember, should only point north, suddenly jumped. It moved. That was the aha moment. The flow of electricity was creating a real, tangible magnetic effect. The two forces weren't separate at all. They were connected. Ørsted's discovery just blew the doors wide open. Suddenly, there were all these new questions. And the biggest one was, okay, if electricity creates this magnetic field, what does this invisible force actually, look like? How can we possibly map something we can't see?
So, first, let's just quickly define what we're talking about. A magnetic field is simply the area around a magnet where its influence, its push or pull, can be felt. Think of it like an invisible bubble of force.
So how on earth do you see something invisible? Well, with a bit of cleverness and some tiny bits of iron. If you sprinkle iron filings near a magnet, they don't just fall randomly. No way. They instantly snap into this beautiful, almost artistic pattern. These are what we call magnetic field lines, and they give us a perfect map of that unseen force.
And these lines aren't chaotic at all. They follow a very strict set of rules. They always flow out of the North Pole and into the South Pole, and they form complete closed loops. And here's the key. Wherever you see the lines bunched up really close together, that's where the field is the strongest. And one more thing, they never ever cross. This beautiful order is what makes magnetism so incredibly useful.
Okay, so we can see the field, that's cool. But can we control it? Can we make it stronger or weaker? Absolutely. And the secret is surprisingly simple. It all comes down to the shape of the wire carrying the current. Let's start with the most basic shape there is, a long, straight wire. When electricity flows through it, the magnetic field it creates forms these perfect concentric circles around the wire, kind of like ripples spreading out in a pond.
But how do you know which way those circles are spinning? Is it clockwise or counterclockwise? Well, there's a really simple trick for that called the right-hand thumb rule. If you imagine grabbing the wire with your right hand and you point your thumb in the same direction the current is flowing, the way your fingers naturally curl around the wire, that's the exact direction of the magnetic field. Pretty cool, huh? Okay, so what happens if we take that straight wire and bend it into a loop? Now this is where it gets really interesting. Every single piece of that wire is now contributing its own little circular magnetic field right into the center of the loop. And all those fields add up, creating a much stronger and straighter field right in the middle.
And you know where this is going, right? If one loop is good, then a bunch of loops must be even better. And that's exactly what a solenoid is. It's just a coil made of many, many turns of wire, usually wrapped around a cylinder. By doing this, we're adding up the magnetic fields from all those loops to make one super strong, uniform magnetic field.
What you end up with is a magnetic field that looks almost identical to a regular old bar magnet. Seriously, it's got a north and a south pole and everything. But the solenoid has a superpower that a normal magnet doesn't. You can turn it on and off just by flipping a switch. That control is the secret behind every electromagnet in the world.
Okay, so we've established that electricity can create a magnetic field. But what happens if we flip that idea on its head?
What if we take a wire that's already got current flowing through it and place it inside another magnetic field? Well, that's when you get the unseen push. That's when you get motion.
So the fundamental idea here is that this is a two-way street. If a current can create a field that pushes on a magnet, then it only makes sense that a magnet's field can push back on that current.
And we can actually see this happen. In this little experiment, we have an aluminum rod just hanging inside a magnet. Nothing's happening. But the second we pass an electric current through that rod, bam, it gets physically pushed. It actually moves. And get this, if you reverse the direction of the current, it gets pushed in the complete opposite direction. This is a direct conversion of electricity into movement.
And, you guessed it, there's a handy rule for predicting which way it's going to go. It's called Fleming's left-hand rule. If you point your forefinger for the magnetic field and your center finger for the current, then your thumb points in the direction of the force, or the motion. This one simple hand rule is the fundamental principle behind every electric motor on the planet.
So, all this talk of invisible fields and forces and hand rules, how does it connect to your daily life? Well, let's bring it all home, literally, and take a look at the wiring that's powering everything in your house right now.
Behind your walls, there's a team of 3 wires working in perfect harmony. You've got the live wire, which is usually red, bringing in the electricity. The neutral wire, which is black, is there to complete the circuit and give that electricity a path to go back. And then there's the green earth wire. Think of that one as your silent bodyguard. It's a safety line that protects you from electric shocks.
But of course, things can sometimes go wrong. If the live and neutral wires accidentally touch, that's a short circuit. Or if you just plug too many things into one outlet, that's overloading. Both cause a dangerous surge of current. And that's where the humble electric fuse comes in. It's a sacrificial hero, a tiny piece of wire designed to melt and break the circuit the instant the current gets too high, preventing damage and maybe even a fire.
And this is why all of it matters. From Ørsted's little compass needle all the way to the rules that govern these invisible fields, these very principles are what make our modern electrified world possible. They aren't just abstract ideas in a textbook, they are silently and safely at work inside your walls right this second.
And for one final thought, get this. This physics isn't just out there in our gadgets and power lines. The exact same principles are at work inside you. The tiny electrical signals, the ion currents traveling along your nerves as you think and move, they are also generating their own tiny magnetic fields. It's an incredible reminder that the fundamental force